Hello, welcome to video number 8. So this may be, I don't know yet, but one of the last videos for Unit 8 gas laws. So we're going to finish up the content. I might do a video on review problems, but this is going to be the last video on new content. So we're going to get started today with a warm-up, and then we'll get into the final gas law. All right, for your warm-up, why don't you take a second and I'll read through these, and then you can pause the video and try to answer those two questions. So this video, I want you to understand how to imagine how gases behave at the molecular level. Because remember, gases are most of the time these invisible things, these invisible molecules that are there. They're all around us, but we can't see them. So this unit, I really want you to be able to understand how those molecules behave, especially when we change things like temperature and pressure, and how those things affect temperature and pressure. So I'm going to read through these two problems and give you a minute to try to answer them. All right, so here I have 4 flasks. They're all the same size, and they're at the same temperature. They contain the same number of molecules. In which flask will the pressure be the highest? And I want you to try to think about why. Okay? And then number 2, each of these flasks contain the same number of gas molecules. In which would the pressure be the highest? So in this case, I'm varying the temperature. Okay? So take a second and try to answer those 2 questions. All right. Number 1. So if I have a bunch of different gases in different containers, and I have them all at the same temperature, and the containers are the same size, the pressure is going to be the same. Okay? So why is that? Okay, why would that pressure be the same? Because remember, gas particles are so small. They're these tiny little particles. They're flying around. It doesn't really matter if you have a big particle versus a small particle. If you have a krypton versus a helium, even though krypton's much bigger than helium, they're both really, really, really small particles. So the individual identity of the particle doesn't matter. Okay, unless you get really advanced into chemistry. But at this level, the individual identity of the particle doesn't matter. Okay? Number 2, each of the flasks contain the same number of gas molecules. In which would the pressure be the highest? So how does temperature affect pressure? And this was Gay-Lussac's law. So remember, as temperature went up, pressure went up. So it should be flask number 4. They have a direct relationship. Why? Because as I have a higher temperature, the particles are moving faster. Therefore, they're running into the sides of a container more often and with more force, causing a greater pressure. All right, so hopefully those 2 went well. Today, I want us to understand gases a little bit more and be able to predict and describe diffusion. Okay, so you might maybe know what this term is, maybe don't. Today, everybody's going to leave here, hopefully, knowing what diffusion is and how to predict the order of diffusion when I have a mixture of gases. So who's going to get out of the container the fastest? Okay? So remember, we've been visualizing, again, these invisible particles. There's gases all around me. There's gases all around you right now. Okay, depending on whether or not you have the oven on or whether or not you're maybe just sprayed some air freshener, we might have somewhat different compositions of gases around us right now. But for the most part, everybody's experiencing the same thing, mostly nitrogen and oxygen around us, and most of us, again, I can't see the gases. But what we've done this unit is we've described these gases with our 4 or 5 main descriptors of gases that I think we did in video 1. So we know gases fill the container, whatever they're in. I'm not going to suddenly walk across the room and not have any air because there's no gas there. Okay, these gases, wherever they are, spread out completely. And it takes time for them to spread out, but they spread out evenly and completely. Okay, if I burn a candle, the one closest to the candle is going to smell it first, but over time it's going to spread out and fill up the whole room. Okay, gases are fluid, they flow all around. Okay, they're not liquid, they just flow all around from one place to another. Gases have a very low density, meaning they spread out completely. Okay, so a lower density means they take up a bigger volume. Okay, gases are compressible because I can push them together. And gases effuse and diffuse. So we talked about that, mentioned this earlier in the unit, but we didn't really define it. So today I want us to define those two terms, diffusion and effusion. The first thing we're going to do is watch a video describing diffusion. Okay, we're going to watch a video describing diffusion. But first, I'm just going to quick define it before we watch that video. So diffusion describes the mixture of gases. Diffuse, remember di means two things mixing together. So if I look at this picture up here, okay, I have two gases in separate rooms. If I were able to break that barrier, what's going to happen is those two gases are going to mix together. And diffusion happens because gas particles move randomly. We can't predict particles' paths. They just move chaotically. Like I've said compared them to kindergartners, okay? Kindergartners on recess are running around chaotically, okay? And turning up the temperature is like giving them more sugar. They're going to run around faster and more chaotically, okay? Also, what I want us to predict today is how size affects how quickly those particles move. In humans, there's going to be plenty of exceptions, okay? But gas particles, there aren't. And I'm going to talk about that in a bit, okay? So we're going to look at the rate of diffusion and how it's affected by temperature and size of particles. But I think that first this video is going to do a great job of introducing the concept. So let's take a second and watch the video. I thought I had it pulled up already, but I guess not. Sorry for the delay.
Water vapor spreads out. Water vapor spreads out into the atmosphere. It's carried by the wind.
Move myself over here.
But it can also spread out of its own accord by a process known as diffusion. Invisible gases behave in the same way. The particles in a gas move randomly in all directions. This helps explain why a gas diffuses from one place to another. You can see diffusion happening on a small scale in the lab using bromine, an orange-coloured gas. Place a jar of air on top of the bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the two gases mix. After half an hour, both containers have a uniform colour. It takes time because the air and the bromine molecules are colliding with themselves and each other. So what would happen if there was no air for the bromine to bump into? All the air has been removed from this apparatus, apart from the flask containing bromine, which is isolated by a tap. Open the tap, and it spreads immediately.
What I like to compare that to is a person, say, trying to get through a house. Your job is to get from the front of the house to the back of the house. Are you going to do it faster if the house is completely empty? Or say they're having a party and it's filled with people? Which scenario would allow you to get through that house faster? Hopefully you're thinking if it's completely empty, I can go right through. And that's the same thing that happens with gas particles. If I have an empty container, the gas particles can fill it up completely because there's nothing there for them to bump into, and they spread out completely and evenly much faster than if there are other gas particles that are in the way, slowing that rate of diffusion.
Watch again. In a vacuum, there's no air to collide with. The bromine diffuses much faster. See how slow the diffusion is when the flask is now full of air. It It takes several minutes to get just this far. This simple setup can be used to compare the rate at which different gases diffuse into air. Nitrogen dioxide gas on the left is similar in colour to bromine on the right, but bromine molecules are much heavier. The lighter nitrogen dioxide diffuses more quickly. We can also compare the diffusion rates of other gases. Ammonia and hydrogen chloride gas are colourless, but when they meet, a white cloud of ammonium chloride forms. A piece of cotton wool soaked in concentrated ammonia solution provides ammonia gas. Concentrated hydrochloric acid provides hydrogen chloride gas. Place the two pieces of cotton wool at opposite ends of a tube and the gases spread out. You can compare the speed at which they approach each other by looking out for a cloud of ammonium chloride. After less than a minute, a white ring begins to form, marking where the gases meet. The white solid is closer to the hydrogen chloride end of the tube.
So, who's moving faster? Is it NH3 or HCl?
On the right. So which gas has travelled faster?
Okay. Hopefully we can say that it's NH3 because it's moved farther. HCl has only moved this distance because it's heavier, therefore it's moving slower. So both gases are spreading out and eventually meeting each other and forming this ring. But NH3 is able to move farther because it's a smaller, lighter particle, molecule.
Another way of monitoring the progress of the gases is to run a piece of damp indicator paper along the tube. Hydrogen chloride gas turns it red. Ammonia turns it blue. Why does ammonia travel faster? Diffusion also happens in liquids. Drop potassium permanganate crystals into water and they begin to dissolve. The purple solution then spreads out. It diffuses through the water. These three tubes containing water are immersed in baths at different temperatures, 0, 20, and 70 degrees Celsius. A crystal of potassium permanganate is placed in each.
Where do you think diffusion would happen the fastest? In the hottest or the coldest beaker?
After 10 minutes, diffusion in the hot water is almost complete. Why does the rate of diffusion appear to be quicker at higher temperatures? What other factors might be involved?
So that's what I want us to learn and understand today. So let's go back to our PowerPoint, okay, and talk a little bit more about diffusion. Okay, so diffusion is the gradual mixing of molecules. Why? Because molecules move chaotically. Because these molecules are flying around chaotically, over time, they're going to spread out. Okay, it's just like, again, a bunch of kindergartners in a room. Okay, naturally, they like to run around and burn off that energy. Okay, they're not all going to sit in one corner. If you just put them in a room together and say you spread out toys or anything, okay, if you just leave them in an empty room, I'm sure over time they're all going to naturally spread out, okay, and run around chaotically. The same thing happens with gases. They move around chaotically. So eventually they fill up whatever container is allowed of them, okay? So there's going to be two things that describe this mixing or filling up of a container. And that's going to be diffusion and effusion. And I want us to understand the difference. Di, remember, means two. So that's going to be when two gases mix together. So here I have side 1 and side 2. If I cut a hole in this, allowing those gas particles to mix together, okay, that is diffusion. Effusion happens when I have a gas and an empty container, and we saw this earlier. And then I let the gas into that empty container, that's when I'm just allowing it to escape or move through a barrier, okay? And which one is faster? Hopefully you know effusion should be a lot faster because there's nothing in the way. It's like moving through an empty house versus a crowded house. Okay? So diffusion is the one we're going to focus on, but effusion, they go hand in hand. They both deal with spreading out. Okay? Now, we can calculate how fast a gas particle is going to diffuse compared to another gas particle. Okay? And it all depends on the ratio of mass. The good news is you're not going to be asked to do these calculations at this level, maybe at a more advanced level, but at this level I just want you to understand who moves fastest and why. But I am going to go over an example. So we do know that kinetic energy is the same for any particles at the same temperature. Okay, as mass goes up, velocity goes down. And you typically, I say this, we can typically imagine that with like a football team, okay? If I have a big lineman, okay, big and he's 400-pound lineman versus a light 150-pound wide receiver, who would you bet would win a foot race, okay? Most of you would probably say, I'd bet the wide receiver. Now, are there exceptions with humans where sometimes these big, giant humans can run really fast? Yeah, there are, okay, but gas particles, there's not really, okay? So with gas particles, light particles move faster, have a higher velocity. Heavier particles move slower, having a slower speed or velocity, okay? And that typically can be applied to humans, but there's some exceptions for humans. For gases, there aren't. Okay, so what I can do is I can rearrange this equation and compare a ratio of velocity of two things to the mass of two things. If I take the square root of the mass of the heavier substances over the lighter substance, I can figure out how much faster the lighter substance is going to move compared to the heavier substance. And I'm going to do a quick example of this so you understand it. You're not going to be using it, but I want you to understand it. Okay, so here we have equal amounts of helium and argon are placed in a porous container. Which gas will escape faster and how much faster? You should be able to explain who's going to escape faster by looking at your periodic table. Who is lighter, helium or argon? And you should say helium. Okay, so helium should move faster. Now the second question, how much faster, I need to use my equation. That equation compares the mass of the heavier substance to the mass of the lighter substance, and it's going to tell me the ratio. So the heavier substance is always going to go on top. So who's the heavier substance? Argon. So I'm going to put argon's molar mass here, and I'm going to put helium's molar mass here. And I'm going to take the square root of that ratio. Okay, so here's argon's molar mass, here's helium's molar mass, and I take the square root of that ratio, and it ends up being 3.16, okay, over 1. So what does that tell me? That tells me how much faster helium is than argon. So helium would diffuse 3.16 times faster than argon if you wanted to calculate mathematically how much faster. At this level, I only want us to understand and be able to describe who escapes faster and why. And remember, the lighter particles diffuse faster. Also, higher temperature diffuse faster because they're moving faster. So today's worksheet is a quick worksheet, just 5 questions and it's multiple choice, okay, on diffusion. It looks like, I'm going to come right back to this, like this. And at the bottom of this worksheet, there's 5 questions that summarize today's lesson, okay? These 5 questions. And if you read through the top, that's going to kind of explain and describe the behavior of gases that we've already described in this unit. But I want you to try to answer these 5 multiple choice questions and share that with me. We're looking at who diffuses faster and why. Okay, and how does temperature affect this rate of diffusion? How does mass affect this rate of diffusion? Okay, also a review question in the middle. Okay, so that's today's homework, worksheet 8.5, diffusion. Okay, remember, lighter particles move faster, hotter particles move faster as well. Okay, so that's today's lesson. I'll see you all at our class meetings. Have a good week.